Day 145, Kirchhoff's laws, homework examples 40 and 41. All right, they're asking us to calculate the battery EMF. Well, EMF, E, the swirly E, means voltage or potential difference. So I'm just going to label that V. So we're looking for a V over here on the left-hand side, the unknown battery. And we don't know if it's more than, less than, or equal to the 12 volts of the other battery. But if you've done enough of these, what you'll notice first off is in this middle branch in our two junctions, there's a junction spot here at the top. I'll call that point A. And then at the bottom, point B. If I'm going from point A to point B, there's 2 amps of current. And since V equals IR, Ohm's law, 2 times 4, we know that this resistor here in the middle is 8 volts. Okay, one of the hardest things to keep track of or to figure out, at least the first few times you're doing these, is which ones are negative voltages and which ones are positive voltages according to the conventions we'll be using. And there's these arrows that we draw. There are the current arrows, arrows that represent current, like the 2 amps here. I'll use a red arrow for that. And, well, let me do another one. That's a branch. And there's a current, most likely from B to A. Not 100% sure it's in this direction, but most likely that's the direction, because I'm going to pick the direction that the battery is actually pushing, because this battery is pushing up, because the positive side of the battery is the long side. So that's the way the battery is pushing the current, at least trying to push the current. If the other battery is not so much larger that it causes current to go backwards through that battery. And the most likely scenario is the 2 batteries are each pushing up. So on the left-hand side here, it's likely that the current in this left-hand branch is going clockwise on that left-hand side. So the currents are coming down from point A towards point B, splitting and going around in a pattern like that. So those red arrows there represent current flow. But then when you apply Kirchhoff's second law, you're going to be going around the circuit from, say, like an A to B, and let me label, say, point C, which is not a junction, but just a reference point, C, D. If I go from A to B to C to D to A, let's label that, loop A, B, C, D, A. As I walk around that loop, either in my mind or I could draw this with another arrow, I'm going to use a different color because this arrow does not represent the currents. It represents the path I'm taking as I go from A to B to C to D to A. As I walk in that direction, which may or may not be with the current. In this case, it happens to be with the current. That's the easiest way to do it, is if that blue arrow, the path you're taking, actually lines up with the currents that are flowing. It makes the problem easier because it follows all the conventions where the resistors will be negative voltages, negative potential differences in the battery. Well, the battery depends on which way the battery is pointing, which in this case is pointing in the direction that I'm drawing that blue arrow. That battery is pointing up, or in other words, counterclockwise current flow in that branch from B to C to D to A. Anyway, in that loop A, B, C, D, A, there's 3 elements, V1 plus V2 plus V3 equals 0. So some of those potentials have to be positive, some have to be negative. I'm going from A to B. I encounter that first resistor, and I'm walking along that blue path in the same direction the current is flowing, the red arrow, straight down. So that gives me the conventional negative 8 volts in that particular resistor. Then I go from B to C to D, and as I'm walking from C to D, all right, I'm going in the direction that the battery is pointing, so that's the conventional plus 12 volts for that battery. And once again, it doesn't really matter what you put here for the third one, although we know it's going to be, it's got to be, plus something equals 0. It's going to have to be, you can see it already, it's going to be negative 4, or if you want to put minus V3 equals 0, because it's the conventional minus some voltage for that resistor, because I'm going in the same direction of the current flow. According to my red arrow, my walking path, the blue arrow, lines up with the red arrow, so I'm going to get the conventional negative voltage for that resistor, and it comes out to be 4 volts. All right. If I was going back in and plugging it all in again, I would have negative 8 plus 12 minus 4 equals 0. So that's the voltage up here, 4 volts. Well, once I know that's 4 volts, right, using V equals IR, I know that this current in that resistor is 0.5 amps, because 4 divided by 8 is 0.5. So I have 0.5 amps. So if we look at point A right now, that junction, we have 0.5 amps going into point A, and we have 2 amps coming down from A to B. That means on the left-hand side here, this must be 1.5 amps, the other current flow, because we have to have 2 amps of current going into point A if there's 2 amps of current coming out of point A. So that's Kirchhoff's first law. I have 1.5 amps. All right, and once again now, if I look at this 10 ohm resistor on the left, if I have 10 ohms and 1.5 amps, V equals IR, therefore that's a 15 volt potential difference for that resistor. And now if I just label my points here, bottom left-hand corner, I'm going to call that E and F. If I take loop A, B, E, F, A, I'll have V1 plus V2 plus V3 generic voltages of 3 elements. When I go from A to B, I'm going with my walking path would be in the same direction as the red arrow, the current path, so I get a negative 8 volts for that particular resistor once again. And as I come around from B to E to F, from E to F, I'm going with the direction that the battery's pointing, negative to positive, so that's going to be your conventional plus that battery voltage. I'll call that V2 in this case, which represents the battery. And then from F to A, I'm going, my walking path is the same as the red arrow current path, so it's going to be minus the 15 volts for that resistor equals 0, so V2 equals 23 volts. That's what we were looking for, the voltage of that particular source, 23 volts. All right, example 41. Once again, these E's, the EMF, that's short for electromotive force, the voltage source, I'm going to call that V1 and V2, V sub 1 and V sub 2. Okay, what I like to do when I look at these problems is I do like to make a quick check of Kirchhoff's first law. In this case, if I look at this junction right here, I'm going to just call that point A, I already noticed that there's 1 amp going to the right through that 8 ohm resistor and 1 amp going down to the 2 ohm resistor to the bottom. That's 1 plus 1 is 2. So I know already that there's 2 amps right here. And immediately, if there's 2 amps there, that's 6 volts. And in this 2 ohm resistor at the very bottom, I know that I have 1 amp and 2 ohms. That's also, well, that's 2 volts, V equals IR. And on the right-hand side, the 8 ohm resistor, V equals IR. I is 1, 8 is the resistance. So that's 8 volts. So I know a lot of the voltages already. Let's label a few more points. Let's call this point B over here. And from the top, I see that there's 2 amps coming from the top branch at the very, very top there, that resistance R. So I have 3 amps total going into that point. I have the 1 amp right here from the 8 ohm resistor, the 2 amps coming down this way from the top, 3 amps going in. So all that's left is I must have 3 amps going this way. All right, that means at this spot, let's call this point over here point C. Here's a junction. A, B, and D are junctions. C is not a junction, but it's a good reference point. So at point D at the bottom here, I have 3 plus 1, I have 4 amps entering, so I must have 4 amps going this way. So I think everything is consistent now, because at this junction over here, let's label some more points. Let's call this E and F. At junction F, I have 4 amps going in, and yes, I have 2 amps going to the right and 2 amps going to the top. So everything is consistent so far with Kirchhoff's first law. And now I look at any particular loop that I would like to pick, and you can see this falls into place very quickly in this particular problem. If I take, say, loop E, F, A, D, E, starting in the lower left-hand corner, going from E to F to A to D to back to E again, there are 3 elements. There's V1 plus V2 plus V3 equals 0, generic statement. There's 3 elements there. So I have my battery, which is V sub 1, and then I go so that's from E to F. From F to A, that's conventional. I'm moving with the current flow to the right, and I'm walking from F to A to the right. So that's minus your 6 volts. And then from A to D will be minus your 2 volts, because I'm going with the current flow arrow, the 1 amp current, which is going straight down, and I'm walking in that direction, so I get minus 2 conventional equals 0. So you can see there that V sub 1 is 8 volts. That's half our problem here. And if we look to the far right? And this will be a good test. Loop A, B, C, D, A. A, B, C, D, A. If I'm going A from B to C to D to A, once again, I'll have three elements, V sub 1 plus V sub 2 plus V sub 3 equals 0. If I'm going from A to B, V sub 1 is my first resistor, the 8 ohm resistor, and I'm going with the current flow, so that's -8 conventional. And I'm going with the direction of the battery here, negative pole to positive pole, so that will be plus V sub 2, which lines up with the actual battery itself. And then from D to A, however, here's an unconventional situation. As I'm walking from D to A, my current arrow, the 1 amp arrow's down from A to D, so that's going to give me, instead of a minus voltage conventional for that resistor, I will have plus 2 volts equals 0. So in that case now, V sub 2 equals 6 volts. That's my potential difference for that particular battery. So there's a good example of an unconventional resistor. As I walk from D to A, I'm going against the arrow pointing down, and I was walking up. So that's 6 volts. All right, now let me do the total outer loop all the way around the outside. I'll need to label a couple points here. Let's call this G and H at the very top. And if I do the loop from G to H to C, well, I'm skipping a few. I'm going around the whole outside. Loop G, H, C, E, G. I went past a couple other spots, B, D, and F, but I went all the way around the outside. And I have 3 elements once again. Generically calling it V1 plus V2 plus V3 equals 0. Going from G to H, my first resistor, unknown voltage, potential difference. I'm calling that V1, applies to that top resistor R. All right, and I'm on V2 at the bottom here, we found out was 6 volts, and we're going with the direction it's pushing, so it's plus 6 volts. And then from E to G, that V sub 1 was 8 volts, plus 8 volts, conventional. So V sub 1 is 14 volts. That's my voltage at the top there, 14 volts. And I know if V is 14 volts, and I use V equals IR at the top, I have 14 equals 2, that's given, times R. R is 7 ohms for that top resistor. There we go. We've got V sub 1, V sub 2, and R.